Now, for the second part of this series, we are to create a Python code for a binary mixture of benzene and toluene, and calculating the dew temperature pressure and the bubble temperature pressure as well. And then later creating some plots for the binary vapor-liquid equilibrium phase diagram for both a constant temperature and a constant pressure. So we're going to go ahead and utilize these derivations that we got in the previous video and put them into our Python code so that we can utilize them to find our actual graphs or plots. Okay. So let's go ahead and start up our code here, and I've only gone and grabbed this CHE tools content here, and we've done this many times, used it many times throughout all my videos, and then NumPy we've utilized many times, and as I said before, we'll be utilizing the root function in this problem, and again, subplots as we want to make some subplots, right? So if we go back and look, actually I'm just going to put these side by side so it is easier to look at the two and copy one from the other. Right? So the first thing that we realize is that we have a binary mixture of benzene and toluene, like we talked before. So we're going to be using our CHE props to recall this. I'm calling the function p and CHE.props. Right? And what we'll be using is benzene and toluene, right? So benzene, toluene, right? Right. There. Sorry, it's just regular brackets. I was confused this. But we have our two properties now. Then, if we keep on seeing, what else do we know? That's all we need to put in at the moment. But we can start off by creating some functions for our bubble temperature and pressure. Okay? So, as we can see, for bubble pressure, we had the mole fraction ratio of the liquid phase multiplied by the pure saturation component in the vapor phase. So, for bubble pressure, actually before that, I'm going to create a list. So I'm going to create x and create an array, p.array, just so that I can save those values, right? We want the 0.3 for the benzene and 0.7 for the toluene, right? Those are the two values that were given for them. Now we can start by creating a function for bubble pressure. So I'm going to define, call it bubble p, capital P, and what it's going to take is the x values, which is that, and temperature, right? And then for what it's going to return, we're going to want to return the sum of these two multiplied together, right? So what I'm going to do is return mp.sum, and so what we have is x multiplied by the purely saturated component in the vapor phase, and that is represented by p.pvapor, right? p.pvap, right? It's taking temperature, right? And we're taking the sum of this, right? Make sure the parentheses are all good. Yeah, we want to return this. So if we go ahead and put bubble p, we want x, and let's say 300 degrees Kelvin. This is the value for the bubble pressure, right? Now we can go ahead and do the same thing for the temperature. So I'm going to go ahead and create a function called bubble t for temperature. And now it's going to take again x, but instead of temperature, it's taking pressure, right? Then here is where we utilize our root function, right? As you can see, for the bubble temperature, it is equal to the summation of the component in the mole fraction in the liquid phase multiplied by this logarithmic scale, right? So we're going to want to create another function within here. I'm going to call it EQ simply for equation, and it's going to have a vector needed. And obviously I'm going to unpack this for being temperature, right, to being the first vector in there, right? Then what we're going to want to return from here is the difference in the pressure, right? We want the difference between the bubble pressure and the actual pressure, and then find the root function between those, right? So what we're going to return here is bubble, I said we want to return the difference in the pressure, so we're going to do bubble P. Obviously, once X and T, we're subtracted from P, right? And obviously, then we're going to want all of this to return a final value of the root function, right? So we're going to want to return a root, right? We have our equation, and as a value, we're going to put 300 Kelvin, right? We said before. Then now, if you want to see if this values are correct, so put bubble temperature X, and for pressure value, we'll return this. And of course, you put dot X, just to receive the value received, and we receive 299.9, which is 300 degrees Kelvin. So we know that this is all good, so I can go ahead delete these cells and run this all over again just to make sure that it is all set up. You see we're all good, right? Now we can go ahead and do their functions for our due pressure and due temperature, right? These two equations that we have down here, right? So before we do that, actually, you see that we are using now the mole fraction ratio in the vapor phase. So now we have to create a new array, right? We'll call this Y value, of course, array, and we're going to use the same values, 0.3 and 0.7. Right? Make sure that's all good. Now we can go ahead and create our function for our due temperature. So go ahead, find a function, go due P for due pressure, and of course it's going to be asking for Y and temperature. Right? As you can see, it's the value of 1 over the summation of the mole fraction components in the vapor phase divided by the purely saturated component in the vapor phase. So what we're going to want to return here is the 1 over the MP sum, right? We want the summation of this, of Y1 of Y divided by the purely saturated component, which is simply this PVAP. So do P dot PVAP Where's temperature? Make sure all these brackets are good. Yeah. And that's all good. We got our due pressure in. Now we can do the same thing, but for our due temperature. So new function, call it due T. Right? And again, we're using Y, but now we're using our pressure again. Right? And again, due T, and we're using Y and pressure. Right, okay. And then here again, this is where our root function comes back into place again. So go ahead and define another function. This time I'm just going to call it EQS. Right. And then again, the same thing. We want to unpack the temperature out of there. So T equals V first. Then again, we want to return the same idea. We want to, as you can see, we want the difference between the two pressures. So we want to return is an array of the due pressure, Y and P, obviously, subtracted from the actual pressure. And then, of course, we're going to go down and finally return the root function of that, of the equations. And again, we're just going to simply use 300 degrees Kelvin for the time being. That's all set. Of course, we can go ahead and check, make sure that this is all good. So do a test, do pressure, we're using Y as always, and now we're using 300 degrees Kelvin. This is the due pressure we're given. Now if we do temperature, with the y value, instead given this pressure, we want to return a value of 300 degrees, which we are given, right? Again, just .xo to give us the value, 300 degrees. So we know that our due pressure and due temperature are in sync and that they are connected well. Now we can go ahead and get started with creating our graphs. So I'm going to go full mode. Actually, for later on purpose, I'm going to put a .xo at the end of both of these so that later on we will not have an issue with those. But now for the graphs, what we're going to want to do is set equally spaced out points. So what I'm going to do is create a new variable, call it z1. I'm going to equally space it out from 0 to 1 by 0.1 decimals. So what I'm going to do is linearly space them out. So I'm going to recall numpy and call line space. Right. And then we're going to want from 0.1 to 1 by 11 equally spaced out values, right? So that if we recall z1, we are given these values. Oh, sorry, should be 0. We're given 0, 0.1, 0.2, an incrementation of 0.1, right? Now we also want to do it for the other way, so what we're going to do is call a new function z2, or a new variable z2, and we're going to subtract it from z1. So that now, if we do z1, z2, we see that they are inversely related. As one increases, the other decreases, right? By the same value. If one has 0, the other has 1, and so on, so that it has a total of 1, right? So that's all good. We also want to go ahead and put in our given values. So if you open this back up, you read we are given a constant temperature and a constant pressure. We're in 393 Kelvin and 150 kilopascals, or 150,000 pascals. So go back in here, call this temperature. We said it's 393 Kelvin, correct? Yes, and 150,000 kilopascals. So pressure is equal to 150 e to the third. Now we have all of our knowns into our values too. So the idea here now is to create an array with our values so that we can plot them out with these values, right? I'm just going to get started with our bubble point, or bubble pressure and due pressure. So they're going to be on the same axis. So if we see bubble pressure, we know, remember, is just simply x multiplied by the P vapor. So what I'm going to do down here is create a new function, a new variable. I'm going to call it bubble underscore P, just to make it a little different. What we're going to do is create an array, right? So we're going to multiply the z1 and z2 values by the P vector, right? So what I'm going to want to do is do z1 multiplied by pvap temperature, and we're using the first array, right? And add it to z2 multiplied by the pvap again, and we're using again t, and now we're using the second for the first array. So now if we recall bubble p, we see our array, right? These are the values that we'll be using for it, right? Now we can do the same thing for our due pressure, right? So for due pressure, I'm just going to do due underscore p again. As you can see, the only difference is in the y value, right? That is the thing that's going to change. So what I'm going to do for this is do 1 all over, and the difference I'm going to do here now is going to be a parentheses. So I'm going to do z1 multiplied by pvap temperature, right? And for this, we're multiplying it again by 0 for the first vector, and then doing it again, so plus z2 multiplied by p dot pvap, right? And then again multiplied by the first. And then that should be all good. There's an issue. I think I might have used a little bit too many parentheses, so let's try to clean this up a little bit. That should be good now. Let's see, there's still an issue. Okay, so I accidentally multiplied this one, should be divided by each other. Right, that should be good now. There's still an issue, probably parentheses by now. Should be all good now. Yes, sorry, so just issue with our parentheses and so on. So now we can go ahead and create our scatter plots, right? So call it fig 1. And we're gonna make subplots. We're gonna have rows equals 1, columns equals 2, right? And then we're going to want to put our bubble pressure and do pressure in here. So we're going to do fig 1 dot add scatter, right? So we add a scatter plot. For x value, we're going to have C1, of course. For y value, we're going to have the bubble pressure. And then for row, we're going to have the first one as well as for a column. Alright, shift enter. Sorry, graph. Right. Do the same thing for the do pressure. Do pressure. Shift enter and we get our two graphs. I think I might be missing parentheses here. Oh, that makes sense. Let's do a parentheses in there. Okay, sorry. There we go. This is our graphs for our pressures for bubble pressure and dew pressure, right? Now we got to do the same thing, but for our dew temperature and bubble temperature, right? So the main idea here now for both the bubble temperature and dew temperature is to create a for loop for each of the different components so that we can continuously update it and give the values in an array. So what I'm going to do is for create a for loop, like I said, for x1 in C1, and then we're going to have x1 or have x2 is equal to 1 minus x1, which is simply what we have here for z2, right? Then from there, actually before, I'm going to make sure that we create the bubble temperature list. Right? We want to create an array and then append it, right? To add it to the end of the list. So create x and recall numpy. And we'll be using x1 and x2, right? And then again, we want to append this. So what we're going to do is bubble t, and we want to append it. We want to add these values towards the end of the list. dot append, and we want to append the original bubble temperature, right? So call bubble T, and we want X pressure for those, right? So submit this, and we recall bubble T. We get our list. Beautiful, right? This is exactly what we wanted to see. Now we can go ahead and do this again, but for our due temperature, right? So I'm going to go ahead and copy and paste this. Now we have due temperature. These are the same, but change these last values. Due temperature append. Due T. Okay. Should be all good now. Run this through, and now we can plot these bubble temperature and due temperature values in here. So now I'm gonna ahead copy and paste this again. We want bubble temperature, and in the second column, and we want to paste that again, and then again second column, but we want due temperature, right? Here we go, shift enter. There's an issue. Oh, of course, sorry. For due temperature, forgot we are using Y instead of the X values. So change all of these X's to Y's. Alright. Due temperature is also Y, right? We can't be putting in X values. So we run that back again, and we get. So I've found my issue here in our due temperature calculation. I use due pressure, and it definitely doesn't take pressure. It takes temperature. So run this all again. It should be all good now. Come down, and there we go. Here on our left side, we have our bubble pressure and due pressure, and on the right side, we have our due temperature and bubble temperature. So you can see we have these curves, and inside is when the vapor liquid region coexist pretty much.